In this video, we'll continue our discussion of section 7.3. These are operations of the Laplace transformation. In this video, we're going to define a new function. It's not a big new idea. You guys have worked with piecewise functions before. We're just going to define it in a different way with some new notation. Okay, so in engineering, in math often as well, we want functions to be turned on and off. What you guys have been taught is this function in piecewise form. You have seen that, okay, we could say this function would be anything less than a, it's going to be a 0. And then once I get to a, it becomes a 1. It like becomes 0 to 1, binary off, on. Okay. How this is defined is with this u. It's called the unit step functions, the heavy side function. Heavy side is I think he's a mathematician, physicist, engineering. I'm not actually sure, but it is a person. Unit step function. It's defined with this u, t minus a, and the a is the on, off, on point. So if I had something like this would be 0 until I got to 3, and then it would be 1 at 3. The 3 is the on, off point. The values are just 0 and 1, never anything else. Okay, so we actually could use this defined to come up with piecewise functions written a different way. So this function, take a look at it. It's g of t from 0 to a. And then at a, we no longer consider g of t. We consider h of t from a on. Now we can use the heaviside function. So take a look at this. From 0 to a, we'll have this g of t. But once I get to a, I want that g of t to go away. So I'm going to turn on a negative g of t, and that's going to make it go away. So at a, that's just 0. What I have underlined. Everything just goes away. But at that point, at a, I want to add in an h of t. So the g of t was on. Once a turned on, it goes away because of the second term. And exactly at that point at a, it adds in an h of t. This is going to allow us to do Laplace of this type of stuff. So what we're going to look at is how to take a Laplace of a unit step function. Okay, let's take a few functions now, put them in terms of this heaviside function, and then we are going to look at a theorem. All right, so let's rewrite this f of t. Okay, this f of t is going to be a 1 all the way up until 4. And then I want to take that 1 away. So at 4, all the way, from 0 to 4, it's going to be a 1, but at 4, it takes that 1 away. And then I'm going to let it be 0. And then I'm going to add a 1 in at u of t minus 5. All right, so there is our function. Take a look at that. If you'd like to plug in a value in, please do. Practice doing this because it really does make the right side of the Laplace easier if we think about it in terms of this instead of doing 3 different problems. All right, there we go. Right, take a look at one more problem like this, and then we'll do a theorem. So we have the f of t function is 0 from 0 to 3 pi over 2, and then the function is sine of t from 3 pi over 2 on. So f of t is going to be 0. I don't need to put anything for 0. All the way to 3 pi over 2, and then I'm going to turn sine of t on at t 3 pi over 2. So this the heaviside function turns it from a 0 to the sine. And that's it for that one. All right, let's go see how these are going to be applied. All right, so we have our second translation theorem. Okay, this says that we are going to, we're going to have a function with t minus a plugged in, and then a heavy side of t minus a. It's very important that you have to match that form. And if that's the case, they said in the book, e to the negative as is the Laplace f of s. I like to think about it this way. This is just the Laplace of the actual function, and then I times it by the e to the negative as. All right, so let's prove this, make sure that we understand where it comes from, and that it's not just coming from magic land. So let's use the definition of Laplace. We have 0 to infinity of e to the negative st times f of t minus a times u of t minus a dt. Okay, so a couple things here. Take a look that this is going to be a zero function until a. So this actually is a to infinity of e to the negative st times f of t minus a. And then I don't need the heaviside function because I picked up at a. The function was 0 all the way up till a, so I didn't need it. So just from a on. Now we're going to do a sub here, and you'll do a u sub like we've been doing. So u is going to be t minus a, like you probably could have guessed, the inside of f. Du is going to just be dt. That's nice. T is u plus a. We're going to use that. Okay, so let's go ahead and convert our integral. This is going to be infinity still at the top. This is a t in the bound, so it's a t equals a. Well, if I put an a plus, oh, hold up, we want a u, and this was a t, there we go. So this was a t, and so we're going to plug it into here. So a minus a would be a 0. So if we plugged a 0 into, or an a into here, a minus a would be 0. I turned t into u. So I get a 0. And then I'm also going to do e to the negative s, and we're going to replace t with u plus a times f of u, and then dt is just du. Right, so using that u sub now, right, I can break it apart. 0 to infinity is e to the negative su, e to the negative sa, f of u du. It's all in terms of u, so I can pull out the e to the negative sa. 0, infinity, e to the negative su, f u du. Okay, that is equal to, we have an e to the negative as, the theorem says up there, so I'm going to flip them. And then that integral is actually just f of s. It's a new definition for f of s. All right, so there's how they came up with that. So it's not out of anywhere. Let's go a little further because you might not see that, or they have this theorem here actually that came out of the book as well. Let me show you how they got to that. If we so we have that the Laplace of f of t minus a times u of t minus a is equal to, we are going to use e to the negative as times the Laplace of f of t. That's the definition that we just came up with. Right, so they're going to extend it to get to here. What if we let f of t equal 1? Well, if that's the case, then f of t minus a is also equal to 1. It's universally 1. So that means that the Laplace of 1 times the heaviside function is equal to e to the negative as times the Laplace of 1. And we have the Laplace of 1 is just over s. So we get e to the negative as over s. So we get that one last definition there. So the Laplace of just the heavy side, that's what we get. Okay. We're going to take a look at 2 examples, and then we'll stop the video and move on to the last application of this, towards the end, I guess. All right, so if we're using this definition, I'm going to write it again. The Laplace of f t minus a times the heavy side is equal to e to the negative as times the Laplace of just the function itself without the shift. Okay, so the thing is, this is why I keep rewriting it. This has to be equal to that. Now, what we have up here, it's almost equal. We're going to go ahead and try to manipulate it to make it look like it. So here's what we have. It'd be really nice if we could get a t minus 2 in the power there. Well, I can flip that and put a negative out front. Now it matches the theorem. I have t minus 2 in both. So this is going to be e, and then it's e to the negative as. A in this case is a 2, so it's going to be negative 2s. Careful with that. The sign thing trips people up. And then we are going to get the Laplace of e to the negative t. Right, so that's what the theorem says right here. Just be very careful. The function that was there, f of t, we took the t minus a out and got e to the negative t. Well, that e to the negative t is just 1 over s plus 1. So we're going to get e to the negative 2s over s plus 1. It is a lot of just pattern recognition matching to make it work. Okay, one more example for this video. All right, we have the Laplace of 3t plus 1 and the heavy side of t minus 1. I'm going to go ahead and write the formula that we came up with, and the theorem really. The Laplace of f of t minus a times the heavy side of t minus a, or its heavy side, just heavy side, is equal to e to the negative as times the Laplace of just f of t. Okay, so the thing is, again, I'm going to keep pointing out, this is what was difficult for me at the beginning, is I would just take off. T minus a has to match. So I am going to write the problem down first. 3t plus 1, they do not match. T minus 1 equals, okay, so what we're going to do is manipulate it. I'm going to do the Laplace, and I'm going to put this in brackets instead of parentheses for a moment. I'm going to do 3 of t minus 1. And I have to think about what's going to go there to make sure that it works out. Like, meaning I didn't change anything. Okay, this is going to end up being a 3t minus 3. And I need to get back to a plus 1 here. So this is going to be a 4, right? That'll give me my 1. So I'm going to put a plus 4 here. And that's how I know it will work out now. Okay, so we didn't change any values. All I did is manipulate it. You can see now that t minus 1 is in both. So I can actually apply the formula. I get e, and then e to the negative a. So it's going to be a negative s. And then we're going to do the Laplace. Actually, we should write it out here. The Laplace of the function without the t minus 1. So I took out the purple thing and put a t back in. Right? Then we know these from our tables. Laplace of 3t is just going to be 3 over s, and then s squared, sorry, and then 4 over s for the constant. And there's our solution. Again, it takes just pattern recognition and understanding these little tricks of plugging in where you want it to be, what you wanted it to look like, and manipulating the arithmetic to work out. It does take practice. Sound like the professor in the room being like some rote memorization, meaning over and over, would be good for you in these types of problems.